Alright, so today we are going to expand the topic of work and apply it to the idea of energy. So now that we know what work is, it's a force applied to an object to move it over some distance. How do we define energy? Energy is kind of a weird concept to wrap your brain around. But energy was usually defined as the ability to do work. So typically, if something had energy, either stored or in its movement, it was able to do work. But we now know not all energies are able to do work in the traditional sense. But right now, we are dealing with mechanical energy, and because we're dealing with mechanical energy, it follows the definition of being able to do work. So we define the kinetic energy, which is a type of mechanical energy, as the energy of an object in motion. Anytime an object has mass and a velocity, it has kinetic energy. So our fancy equation for kinetic energy is the kinetic energy of an object is equal to 1/2 times its mass times velocity squared. So remember, when you're using this square, it only applies to the v. It does not apply to the whole thing. And it turns out energy has the same units as work. Because energy is the ability to do work, they'll have the same units. So if we think about this equation, kinetic energy of an object is 1/2 times the mass times velocity squared, what has a greater effect on the amount of kinetic energy of an object? The mass or the velocity? Well, if we have kinetic energy equals 1/2 mv squared, and we multiply the mass by 2, that's like multiplying the other side by 2. When we multiply one side by 2, we have to do the same thing to the other side. So the other side is also multiplied by 2. However, if we do the same thing for velocity, remember we have these little parentheses here. So we actually end up multiplying by 2 squared, which is 4. So velocity, or the speed of an object, has a greater effect on the kinetic energy of something than its mass does. So the faster something travels, the more able it is to do work. So let's use this information in a problem. A 145-gram baseball is thrown so that it acquires a speed of 25 meters per second. What is its kinetic energy, and how much work is done? Well, we have a baseball, and it's moving at 25 meters per second, and it has a mass of 0.145 kilograms. Remember, we always work in kilograms. So we use our new equation, 1/2 mv squared, and we just plug in what we know. 1/2 times the mass, which is 0.145, times the velocity squared, 25 squared, is 45 joules. So this is the amount of kinetic energy of the baseball. But how will we know how much work is done? Well, it turns out because mechanical energy is the ability to do work, the net work done on an object equals the change in its kinetic energy. So net work equals change in kinetic energy. And this is a really important point. We're actually going to talk about it a little bit more. But because this ball started at 0, we can assume the ball was not moving before it was thrown. And it moved up to 25 meters per second, at which point it had 45 joules of kinetic energy. The change in that kinetic energy was 45 joules, 0 to 45. So it turns out the net work done on this baseball is also 45 joules. So the net work done on an object is equal to the change in kinetic energy of an object. This is called the WorkEnergy Theorem. And it's really, really important. The net force times the distance something travels is equal to its change in kinetic energy. So if the net work done is positive, that means the kinetic energy increases. And if the net work done is negative, the kinetic energy decreases. And because work and kinetic energy are equated, meaning one is equal to the other, they have to have the same units. So let's do a little bit of a sample problem. There's a 2,000 kilogram car moving at 30 miles per hour, and it smashes into a tree. And it collapses 1 foot. What force will be exerted on the driver? Well, the very first thing that you have to notice is that we have some really funky units here. We have kilograms for mass, that's good, but we have miles per hour for velocity, and we have 1 foot for a distance. So we're going to have to change a couple of these. Let's start with 30 miles per hour. We have to change this to meters per second. So we set up our conversion factor like we did weeks and weeks and weeks ago. And we know that there are 1.6 kilometers in 1 mile. And there are 1,000 meters in every 1 kilometer. And there are 60 minutes in an hour, and there are 60 seconds in each of those minutes. So there are actually 3,600, or 60 times 60, seconds in 1 hour. So if we do some canceling here, when we do the math out, we find that 30 miles per hour is 13.3 meters per second. So we've got that in meters per second. That's good. And it turns out, I just happen to know this off the top of my head, that 1 foot is equal to 0.3125 meters. So now we have everything in the correct SI units, meters, meters per second, kilograms. We're all good. Now let's figure out what force is exerted on this driver. Well, in order to figure that out, we should really look at the change in energy of this automobile, right? We know that the work done on an object is the force times the distance traveled by that object, which is also equal to the change in kinetic energy. And if we write that out, that's 1/2 mass velocity final squared minus 1/2 mass velocity initial squared. Right? Because a change is final minus initial. And we are going to assume that the mass of this car doesn't change. None of the bits are falling off. It's just all crunched together. So to simplify this a little bit, we have force times distance equals 1/2 m v final squared minus 1/2 m v initial squared. And we can start plugging in numbers. We are trying to figure out the force applied to this guy. But we already know how far he traveled, right? The car crunches 1 foot before it comes to a stop. So the total distance traveled is 1 foot, or 0.3125 meters. This car's final velocity is 0. It comes to a stop. So we have 0 squared here, and the initial velocity of the car is the calculation that we did a little bit earlier. It's 13.3 meters per second, and we'll square that. So now when you plug this into your calculator, you find that force times 0.3125 meters is equal to a change in kinetic energy of negative 13,333. Remember, the units are joules. So this is the change in kinetic energy of this vehicle. Over 13,000 joules. But we have one more step left. In order to find the force applied to this man, we have to divide both sides by 0.3125. So the force applied to the man in this car is 42,665.6 newtons. That's ridiculous. That is crazy. I have a weight of about 600 newtons. So if we take 42,665, divide by 600, he experiences 71 times my weight in this car. That is crazy. And it turns out that this man has the same amount of force applied to him. The only difference between wearing a seatbelt and not wearing a seatbelt is that this force will be applied to you through your seatbelt, and it will be applied over the amount of time it takes for the car to crunch, if you're wearing it. If you're not, you're still going to feel that force, but you're going to feel it all at once when you hit the windshield. So this is another reason, a good reason of why you should wear your seatbelt when you're driving in a car. Life lessons through physics. So go ahead and try some of these questions for homework and have them ready to hand in next time I see you. Is it possible to do work on an object that remains at rest? Why or why not? And what is the kinetic energy of a great white shark, which has a mass of 1,000 kilograms, moving at a top velocity of 40 kilometers per hour? If he then slows to 20 kilometers per hour, how much work did he do? And I'm just going to give you a little hint here. You'll have to do a few conversions. So good luck with that.